All right, I think we're going here. Hi again, my name is Andrew Farrington. If you didn't remember, we're going to dive right into it. So we left off, we were going to start on the actual transformer protection aspects of transformer protection. The most, I would say, important to understand piece of transformer protection is transformer differential protection. This is usually used for transformers that are 10 MVA or greater. Between 5 and 10 MVA, you may or may not have transformer differential protection, and lower than 5 MVA, you're usually looking at a fused transformer, especially if it's a power transformer, not like a generator. Generators may have transformer differential protection even below 5 MVA, but for distribution and power transformers, you're usually looking at around 10 MVA and greater. You start to protect the transformer with breakers and differential protection and overcurrent protection rather than fuses. Differential protection has some great benefits. It's very fast protection, and when it's designed and set correctly, it's very secure and reliable, so it's very good protection, so we like it. The relay should trip a transformer differential lockout relay that'll be used to isolate the transformer and prevent re-energization until crews can inspect the transformer. Because it's so fast and secure and reliable, if the transformer differential relay operates, you know that the fault is in the transformer zone of protection. So you want to lock it out, trip the high and low side breakers, and prevent them from being closed using a lockout relay in order to isolate the transformer and allow crews to inspect it. Transformers are obviously very valuable pieces of equipment, so you don't want to re-energize them if they're faulted without having somebody inspect it. So that's why we use the lockout relay. At a high level, transformer differential protection is very similar to bus differential protection. It operates on Kirchhoff's current law. The amount of current through the transformer, when added together in a manner such as this, similar to bus differential relays, it should equal 0 unless there's a problem inside the zone of protection, i.e. there's a transformer fault. So I'm going to kind of piggyback on what Brandon has already described for bus differential protection, but transformer protection also has additional considerations because the transformer has a turns ratio, so the currents aren't the same on the high side and the low side of the transformer, and there's also potentially a phase shift, and you have CTs that may be wired differently because of the transformer winding configurations. So those are things that we need to consider when we set the transformer differential protection that aren't considerations for bus differential protection. But the theory is very similar. So hopefully you'll see that once we account for those differences, it's basically the same thing. We also need to consider inrush and harmonics when we're protecting transformers. Also, things you don't have to worry about when you're protecting a bus. So what we want to start with is a traditional high impedance transformer differential protection, or not high impedance, electromechanical differential protection, because the theory is very helpful in understanding how you apply that in a more modern relay. And the microprocessor-based relays are really just replicating what was done historically with electromechanical relays. So if you understand how to set an electromechanical relay, you should be able to understand how to set a digital relay. And we'll go through an example of both, but the theory is important. So we're going to start with an electromechanical relay. What you want to do is have your CTs, the CT ratios, essentially undo the differences of the transformer. What do I mean by that? Well, if you have a turns ratio of N1 to N2, say this is 10 to 1, ideally you'd have the CTs have a ratio where this is 10 times higher than this ratio. Especially for a YY transformer, that math is easy because basically if you have 1 amp in, you get 10 amps out, and so you can adjust those CT ratios such that the current that actually flows to the relay is equal. So that's great. But you also have to consider the winding differences for this transformer. So this is a delta Y transformer. So what would historically be done for a delta Y transformer is to connect the delta side of the transformer would have CTs connected in a Y configuration, and then the Y side of the transformer would have CTs that are connected in a delta configuration. And the connections of these CTs is important because you want to connect the polarity dots such that they undo the phase shift of the transformer. So you need to pay attention to that. And if you do that correctly, then the phase shift for the currents seen by the differential relay will be undone by the CTs such that the currents can be directly compared, which is what we want. You also need to account for the fact that these CTs are connected in a delta so that the current seen by the relay is going to be the square root of 3 higher than the actual phase current. So this is just like we went over this back here. You know, the current seen, excuse me, for a delta, the current seen by the winding is the square root of 3 higher than the current seen by the phase. So we're undoing that with our CT connection, our delta CT connection. I think others have already covered how that works. So you just want to know that this is going to be the square root of 3 higher than the actual current seen by any individual CT. And again, that has the nice benefit of undoing, quote unquote, the additional phase current seen by the Y side than you would see by the delta side. So you want to size the CTs so that the CTR2, which is the low side CT, is basically equal to, or CTR2 divided by CTR1 is basically equal to the N1 divided by N2 ratio. Okay, and then if you connect the Y winding CTs in a delta and the delta winding CTs in a Y, you're going to undo that phase shift and you're going to account for the increased current on the Y side of the transformer. The relay itself, it's not often that you can actually connect the CTs to ideally match the inverse turns ratio of the transformer. So the electromechanical differential relay has various taps for both the high side and the low side that you can use to account for any differences between the ideal ratio for the CTs as compared to the ratio of the transformer. So we'll get into I think a good example of that here. So this was from a Schweitzer protection class I did a dozen years ago or so. And we're going to walk through this example, and this will be very similar to one of your homework problems. So rely on this to go back and recreate what the homework problem is. Like I said, in practice, your ideal CT ratio is not going to actually match the turns ratio of the transformer. So you've got different taps that you can use. And what you're ideally looking for is that the current seen on the high side of the transformer divided by the tap for the incoming, this is the tap 1 setting for this relay. The current here divided by this tap is going to be equal to the current here divided by the tap on receiving the low side current. So that's what we're looking for ideally. And this, again, this is a good example. So what we did, or what I did, is take the 30 MVA transformer rating and calculate what the phase current will be for that. And I included the angles here. I assumed that the low side current was at an angle of 0, and then I included all the angles here so that I can get the vector summation so that you can actually see that the current seen by the relay is actually in phase. So in practice, as long as you set up your CTs correctly here, you don't need to worry about that. But I thought it was good to include anyway. And you calculate the phase current for the high side and the phase current for the low side. And those calculations are down here. So you take the 30 MVA divided by the square root of 3, and then the high side voltage, phase-to-phase voltage rating, and you get 150.6 amps. And then what you want to do is you want to select the CT ratio that is the next highest to that. And so that's to get above the thermal rating of the CT, right? You don't want the CT to get burned up due to load current. Once you've selected that CT ratio, you can then do the same thing for the low side. So you can take the 30 MVA divided by the square root of 3 and the low side voltage rating, and then you get 1255 amps in this example. And then again, you'd select the next highest CT ratio, which is 1400 to 5. Once you've got those CT ratios selected, then you can calculate what current will be seen by the relay for the high side and the low side, right? So 150 divided by the CT ratio of 205 gives you 3.75 amps secondary here. And then for this current, you need to make sure that you take the square root of 3 higher current, because these CTs are wired in delta. So this current is going to be the square root of 3 higher. So once you get that, then you can see that the currents into the relay in this example again is 3.75 amps coming from the high side and 7.75 amps coming from the low side. And the ratio of the low side current to the high side current is about 2.05. Okay, and again, all of that's written here. Should be a very good example for you to follow for your homework problem. This table is, these are the different taps that are available for this particular relay. So there are 8 taps available for tap 2, and then this is tap 1. And this table gives you the ratio of tap 2 to tap 1. So obviously 2.9 divided by 2.9 is 1. And what you're trying to do is find a ratio on the table that is as close as possible to the ratio that you calculated. This will give you the minimum amount of mismatch and the lowest error in the current seen by the relay, so that you can get that differential operate current to a minimum. So the closest ratio to 2.05 in this case was 2.071, which was a tap 2 of 8.7 and a tap 1 of 4.2. So that was the answer. I kind of wrote that out here. So tap 2 was 8.7, tap 1 was 4.2, and you can then put that back into this equation and make sure that that's the minimum difference, right? This is the ideal, and so you can calculate that mismatch and make sure that you've selected the right ratio of tap 1 to tap 2. So this is the general practice for an electromechanical relay, how you set it, how you select the CT ratios, how you select the tap settings, and get the best differential protection that you can. For newer installations, you're probably going to have an electromechanical, a microprocessor-based relay instead of an electromechanical relay, and you're going to have different considerations, but it all, again, goes back to that initial electromechanical relay example that we just went through. You'll you'll have different considerations, but fundamentally, if you understand this, you'll understand the microprocessor-based application. I decided to just go through an example like I did here of a delta Y transformer because, like I mentioned earlier, that's mostly what you're going to run into. This is an example of like when I was reviewing materials to prepare for this course. There are all kinds of different unique examples that you might run into, and I'm going to leave that to you guys. If you have a unique example, you're going to have to do the research. You're going to have to find an application guide for that particular installation, or you're going to have to refer to the instruction book for the relay manual for the particular relay you're looking at. But in general, if you understand this, you know what goes into it. That's what you're going to need in 90% of your applications. So now we're going to run through an example of how to set a microprocessor-based relay, and I chose an SEL 787 as an example. Things that you're always going to need to set, regardless of what type of relay you're looking at, are the CT ratios, obviously, the tap settings, which we just kind of covered how to do that here. The theory is the same. Often for microprocessor-based relays, the tap settings will actually be calculated for you automatically. You take the transformer's top rating, its maximum rating, and the CT ratios, and then it'll just calculate the tap settings for you automatically, which is pretty handy, but you'll want to make sure that they're calculated correctly. Then you'll want to set the winding configuration settings, or they're also known as compensation settings. And then you'll need to determine what the operate current or slope characteristics are. And things that are often included as like additional features in a microprocessor-based relay are things like the unrestrained operate current, which is a setting just like bus differential relaying. Usually you operate on a slope that relates your operate current to a restraint current. Sometimes the current, the operate current is so high that it's basically impossible or impractical that would ever be a through fault current. And so the relay doesn't need to wait for the calculations of that slope characteristic, and you can just trip immediately. So that's the unrestrained operate current versus the restrained operate current, which is operating on that slope. And then you might also want to consider harmonic restraint or blocking settings, and we'll talk about that. So let's run through a 787 example. Last year, this was a live class, so I had the class tell me what settings that they thought were appropriate based on this example, which I thought was helpful, but we obviously can't do that, so I'll just have to go through it myself. So hopefully it's not boring. This is our transformer that we're going to protect. One of the things that I really want to point out here is that the CT connections to our 787 relay are what you would expect. They're standard connections, right? So the A phase CT is wired into the A phase current input, B to B, C to C, and so on. Winding 1 is on the high side of the transformer, the delta side of the transformer, and winding 2 is on the low side of the transformer, which is pretty typical. but your relay may not be set up that way, right? So you need to pay attention to this. Like I said, the transformer is a delta Y transformer. Both of the CTs are wired in a Y configuration. Neither is wired in a delta. That'll be important for our settings in a moment, but you need to pay attention to that. And then, like I said, on the low side, we have the low side A current wired into the A current input, B to B, and C to C. And the polarity dots are all as you would expect. You guys have had, the elementary diagram classes and relay one line diagram classes, so you know that this is typical, but if that's not the way that your relay is wired, it's going to change these settings. So don't take it for granted that that's the way that your relay is wired. Last year, I used an example, what I think is an interesting example from CMP. Their 345 kV system has a phasing of ABC, and their 115 kV system has a phasing of 1, 2, 3. And A is not related to phase 1. A is actually phase 2, C is phase 3, and A is phase 1. C is phase 1, excuse me. So for their 345 to 115 kV auto transformers, they actually wire in A to current input A, B to current input B, and C to current input C. And then they do 1 to current input 1 to the A current input, B, B to 2, and then C to 3, or 3 to C. But those currents don't relate to each other because they're shifted by 120 degrees. So you need to account for that in the compensation settings of the relay. And we'll get into more details on that, but I just want to bring that up to you because there's sometimes more details that you need about the system than just the elementary diagram, right? That would be extremely confusing if you didn't understand that and know that going into setting the relay, that you need to shift everything by 120 degrees. So just be aware of that. You need to look at the transformer winding configuration. You need to look at the phase connections of all the CTs. You need to look at the relay inputs, and all of that is going to go into these compensation settings. This is a simplified example. This is what you're going to encounter most of the time. I just want to make sure that you're aware of those other considerations so that you don't oversimplify it if you're ever asked to set one of these relays. So these here are the settings that you're basically always going to have to set regardless of the relay manufacturer or model. And then these are the ones that are kind of subject to the type of relay that you're using. So winding 1 is the CT connection for winding 1, which we already talked about this. Both CTs are wired in a Y. So you'd set the winding 1 CT connection to Y and the winding 2 CT connection to Y. The winding 1 phase CT ratio, well, that's pretty self-evident. It's not actually depicted on here, but you'd select the CT ratio for that particular CT. How do you determine the CT ratio? We kind of covered that. You want to make sure that you're not limiting the thermal capabilities of the transformer with the CT ratio that you're connecting. And you generally, well, it depends on the utility. Some generally want it to be set lower so that you have a better accuracy, and some generally want the CT ratio to be set higher so that you can maximize the amount of loadability for the transformer in emergency situations. So the point with the setting is you just set the CT ratio to what the CT ratio is. So those are kind of self-evident. Then you've got the transformer's maximum capacity. in MVA. So this, you'd go to the nameplate and you'd look at the maximum transformer rating, which is 10 MVA. So that's what you'd set that setting to. Then this setting here is whether or not you need to define the CT compensation, and yes or no. Generally, you're going to have to set that to yes. And what that means is that the currents that are seen by each CT cannot be directly related by the relay without some sort of compensation. How do we know that there's a compensation, that it needs to be made? Well, this is a delta Y transformer. So that has a couple properties. We know that there's going to be a 30 degrees phase shift one way or the other. So we need to account for that. That would be we need to set that to yes to account for that phase shift. The other one is that there is a ground source within the zone of protection. And what do I mean by that? This is a Y winding that is solidly grounded. So if we have a single line of ground fault out here beyond these CTs, there's going to be zero sequence fault current that's provided to that fault. And we talked about how the zero sequence fault current circulates in the delta side, and that the transformer is actually acting as a source of zero sequence fault current and not a path through which zero sequence fault current can flow. So it's actually originating here in that delta winding and then being sourced through the Y windings neutral connection to the fault. So if this CT is seeing that zero sequence fault current, but these CTs do not see that zero sequence fault current because it's circulating here in the delta and isn't measured by these CTs. If you don't account for that in your differential protection settings, then the relay is going to trip for an out of section fault potentially. We don't want that. So those are the two criteria as to whether or not you need to set this compensation setting to yes. Okay. So in both cases here, we have that phase shift. We have a source of zero sequence fault current within the zone of protection, so we need to set that to Y. It's also possible that you might have like a grounding transformer within the zone of protection. That's less common. It's usually because you have a delta Y grounded transformer. If this were a YY transformer that was grounded on both sides, you may not need these compensation settings because you don't have a phase shift with a YY transformer, and because both sides are Y windings with a grounded neutral, the only way that zero sequence current can flow through the transformer is if it flows through these CTs and then back out these CTs. So that's a case where you may be able to get away with setting that to no or N. But generally, you're going to have to account for some sort of compensation. Then we have the winding 1 and winding 2 compensation settings. You can see that the available range is between 0 and 12. We'll talk about that in the coming slides, so just put that on hold for now. But that's looking at that phase angle shift for a DY1 or DY11 transformer, and this is where we account for that. Then we have the winding 1 line-to-line voltage and the winding 2 line-to-line voltage. For our transformer, winding 1 is the high voltage winding, which is 13.8 kV, and then the low voltage winding is 4160. So our settings would be 13.8 kV and 4.16 kV. I think I got ahead of myself here. I was just kind of listing all of the settings. I actually have slides that cover all of this, so don't be intimidated. This slide goes through each of these individual settings, like we just talked about, and hopefully you'll find that what I wrote is consistent with what I just said. And next we'll talk about the winding 1 and 2 CT compensation settings. All right, so we know from our previous class that this is a DY1 transformer, again, because if you brought this X1 phasor over to this, the X1 phasor would plot out here at 180 degrees, right? Because the 0, 90, 180. It would plot right over here. And so if you had a counterclockwise rotation, H1 would show up before X1 by 30 degrees. So there's a 30-degree phase shift. The Y winding is lagging by 30 degrees. So it's a DY1 transformer. We could also look at the winding connections and see that the polarity of H1 is connected to the non-polarity of H2, which is a DAB transformer. So again, that would be the Y winding has a 30-degree lag to the delta winding. Yeah, so what information, I got ahead of myself again. What information do we need in order to set that compensation setting? We need the transformer vector diagram, which in this case is a DOI1, as we just went over. You also need the AC schematic, which shows the system phase to transformer bushing connections. So here we have A is connected to H1, B is connected to H2, C is connected to H3. Pretty simple, but you may not have these phase to bushing connections, right? You could have a different rotation. So that would play into whether or not this is actually a DY1 transformer when connected to the grid, or if it's DY11. Depends on that sequence. Here it's ABC, so it's going to match the nameplate. You also need to know what the CT connections are, whether it's Y configured CT or a delta connected configured CT, and whether or not those CTs are actually connected where phase A is into the A input, like we talked about. And yeah, the CT to relay connections, which is what I was just saying. So for the transformer we have, the connections are A to H1, B to H2, and C to H3, which is very simple. And then the phase shift depends on those connections. So I'm just going over that again here in more detail. I guess I should scroll through the slides before I start trying to ad lib and talk about it. So very simple. So this is great. All of the connections are standard and in accordance with good engineering practice. See the previous lectures on relay one lines and AC schematics. This makes it much easier to set our relay. Many applications do not conform to the standard connections, but compensation settings can typically be adapted to fit any application if needed. Here are the general guidelines to selecting the appropriate compensation settings. We need to determine the phase shift as seen by the relay, which is determined by the phase shift in the primary load current. And if there are non-standard CT connections, then we need to select the reference winding and the associated relay terminal. So this is from the SEL 787 instruction book. And it says, if a delta winding exists and is wired into the relay, choose it as the reference winding. And we do have that, right? Winding 1 is connected to the winding 1, relay winding 1 is connected to winding 1 of the transformer, which is our delta connection. So we're going to use that as our reference winding. And then we're going to select the setting of WN. This is our winding 1, so it'll be W1 CTC equals 0 for the compensation of the delta winding. And if a grounding transformer, I should have said grounding transformer exists in the delta side of the transformer and is set within the zone of protection, select the winding of, select the setting of winding 1 CTC equals 12. So this is based on the clock position, like we talked about. 0 and 12 are kind of used interchangeably because they're both, vertical from the origin. So what's the difference? The setting of 0 does not remove the 0 sequence current from the current going into the relay. Okay, a setting of 12 does. Why would you use one versus the other? if you had a grounding transformer between these CTs and the transformer winding, and you had a single line to ground fault over here, that grounding transformer would source fault current through those CTs. But the fault is external to the zone of protection, and it's obviously not going to be seen by the low side CTs because the zero sequence current can't flow out of this delta. It's only sourced by that grounding transformer. So you need to remove that current from the differential calculation, or you're going to misoperate for an out of section fault. So 12 removes that, 0 does not. In our application, we only have the delta winding. We don't have a source of zero sequence current on the high side, so we can use a setting of 0. Okay. Here, you wouldn't want to use 0 because there is a source of zero sequence fault current, the transformer neutral, sourced from the delta winding. So you'd have to use a setting of 12. If these, pretending these were in phase, we obviously know that they're not because there's a phase shift, but just pretending that they were in phase, you'd have to use a setting of 12 to remove that that zero sequence current from your differential calculation, because if there's a single line to ground fault here, this CT is going to see that zero sequence current. These CTs are not, so you have to remove it. If a delta winding does not exist, select one of the Y windings as the reference and choose a setting of W1 CTC equals 11 for the compensation. And the reason you use 11 and not, like, say it was a this transformer was a Y winding with a grounded neutral, just like this one, they don't want you to use 12 and 12, which would be what I would intuit, you know, yeah, there's no phase shift, so we'll just select them both here, and then we'll remove the zero sequence. Although if it was Y grounded on both sides, you wouldn't actually need to do that because it would be seen by both CTs. But, you know, just saying, it might make sense to make them both 12. Well, it doesn't want you to do that because there's an issue with the matrix math used for the differential calculations, and you can get a divide by 0 error that can cause the relay to misoperate. So it would prefer the relay, and I think most microprocessor based relays are similar because they all have this divide by 0 error. What they want you to do is actually set them both to 11. So the compensation is still the same, but they want you to use those odd numbered matrices whenever possible, because it avoids that divide by 0 error that you can get with even numbered matrices. And then step 3 is to determine the required compensation settings for all other windings. So select setting 0 for delta windings, use odd matrices for compensating Y windings, avoid the use of even matrices when possible, which is what I just said. All right, so in our case, the transformer has a standard phase to bushing connections, and to determine our compensation settings, we look at the phase shift as seen by the relay. The phase shift in the primary load current as is such that the low voltage winding lags the high voltage winding by 30 degrees, as we can see by looking at the vector diagram, and there are no non-standard CT connections. So here, I guess I'll read what the relay manual says and then why I think of it differently. So the way that the manual tells you to select the compensation settings is well, we're going to select the delta winding with a setting of 0, and then that step 3 that we just covered here, the manual says to determine that IAW2 must be rotated 30 degrees, which is one multiple of 30 degrees, in the counterclockwise direction for a system with A, B, C phase rotation in order for IAW2 current to be 180 degrees out of phase with IAW1, therefore set to W2CTC equals 1. That's confusing to me. I'm going to say that in 99% of applications that you're going to run into where you have a delta Y transformer with standard CT connections and a a standard transformer phasing of either DY1 or DY11, what you just need to do is set the delta winding to 0 and then set the Y winding to the clock position that corresponds to the phase shift for the transformer. So in our case, it would be 1. So you can see that that results in the same answer. Okay. So this is how I think of it, right? The IA, capital A, is the primary current, and the Y winding current lags by 30 degrees. That's the 1 o'clock position. This is 12 or 0, and then you have the 1 o'clock position, so you just set it to 0 and 1. Most of the time, that's all the thought that goes into it. You just need to be aware of the other times when you might not have a standard CT connection or a non-standard transformer phase shift. Okay. That's why it goes through this long explanation. What they're driving at is for load current through the transformer. Say current going through this phase into this winding and then coming out of this winding and going into that phase. Because the way that the CTs are connected, this polarity connection here goes, they're pointing in opposite directions. They're pointing towards the protected piece of equipment, which is what we want. But when there's load current, the current is going into the non-polarity side of this CT. So what's actually going into the relay input is the inverse of, the current that's going into the transformer. So it actually, what the relay is actually seeing is this. And so in order to make those two currents 180 degrees out of phase for load current, such that when you add them together, they equal 0, you would need to advance this in the counterclockwise rotation by 30 degrees so that they're 180 degrees out. Again, so that if you just added what the relay is seeing, it equals 0. So effectively, it's the same thing. The only time you really need to worry about this is, again, when you have non-standard connections or a non-standard transformer. Most of the time, you could just say, delta is 0. I know what my Y winding connection is, and it's a DY11 transformer, so I'll set it to 11, or it's a DY1 transformer, and I'll set it to 1. Okay, and that's what this note is talking about. So read that if my explanation was confusing, and hopefully that will help. Then we get into the other settings that these are kind of dependent upon the type of relay you have, okay? Or most of them are dependent upon the type of relay you have. Obviously, we want to enable the transformer differential protection, so we're going to set E87 to Y. The winding 1 current tap for this relay, like I said, sometimes they calculate it for you automatically. This relay does that, so this isn't even settable. It's grayed out in the settings file. It's automatically calculated. You put in the top rating of the transformer, you put in your CT ratios, you put in your winding configuration, and it will give you the current taps. But the theory for this was covered in the electromechanical example. Then you set your operate current. That'll be dependent upon the the relay manufacturer's recommendations, and also if the transformer has particular recommendations. Sometimes they may say the operate current for a three-legged core transformer is different than the recommended operate current setting for a four-legged core transformer. Look at your relay manual. The 787 relay manual says that you should set it as low as possible in about the 0.2 to 0.3 range. That's a per unit setting. Okay, so what's the actual current seen by the CT that causes it to operate? You take that per unit setting and then you multiply it by the tap for that particular CT. So if you wanted to know what the high side current needed to be in order for the relay to operate, you'd take say the setting was 0.2, you take that 0.2, you'd multiply it by tap 1, and then you can multiply that by CT ratio 1, and you can calculate the primary amount of fault current that would be required for the relay to operate. All right, when determining your operate current in primary amps, note that the setting is a multiple of the tap setting. Yeah, exactly. So the operate current in primary amps is the setting times the tap times the CT ratio. Yeah, just like I said. Then the next two settings here, the 87AP and 87AD settings, those are optional. This is to basically give you an alarm if you have differential current that is say above negligible, but below the actual operate quantity. So Schweitzer basically says set it less than the operate quantity, typically like half of it. And this is something that if you're ever setting a transformer differential relay for the first time, that the transformer is going to service, so you've set up the CT ratios and the compensation settings, you should really try, if you're not there on site yourself, you should try and get the commissioning engineer to look at the operate current on the relay after it's in service and servicing load, because the operate current should be essentially zero. Ideally, it's zero. There may be a little bit because of mismatch or inaccuracies in the CT, the tolerances within tolerance or whatever, right? So it should be zero or 0.01 per unit or something that's very low. If you've set your CT compensation settings incorrectly or your transformer winding configuration settings incorrectly, there will be operate current, and it should be, close to the restraint current. And that's a bad sign. And it happens all the time, because you can energize the transformer for that. And for load current, the operate current may be low enough that it doesn't exceed the restraint value on that curve. Okay, so your operate to restraint current isn't above that. But then you might have an out of section fault a year later, where now your operate current, because you've set the relay incorrectly, gets above that curve, and the transformer differential relay trips when it shouldn't have, when you should have had downstream protection operate. And it's happened. Luckily it hasn't happened to me very often, but it has happened to me, usually because the transformer connections were not per the drawings, which, not much you could do about that. But if it was like for the instance I'm thinking of was for a mobile transformer, and so it was a temporary thing, and anyway, it happens. So I learned from that if you can, talk to the person that's commissioning it and get an in-service reading after they've closed in the transformer and it's carrying load. Hey, go look at the operate current. Is it zero or is it not zero? Because if it's not zero, I want to know so that I can try and figure out what happened. It may be they left a CT shorted. I've seen that happen. It may be that I don't know, there was a wiring error or something, or I don't know. There could be any number of explanations, but you want to know that because if it's a setting that you've come up with, you don't want to be the person that caused the transformer differential relay to trip for an out of section fault. Taking out customers, they go there, the transformer lockout relay is rolled. Now they're going, oh, geez, is there a problem in the transformer? It's just not a good situation to be in. So just a word of caution. This, these settings that for that alarm, that's what that's intended to cover. It's intended to identify mistakes, or maybe a CT is deteriorating and you're approaching that operate current. So you just want to be aware of that so they can send out somebody to look at it and go, hey, what's going on here, and troubleshoot the problem. So the 87AP setting is the pickup, and then the D is the delay. So um, then we want to set the slope settings, and these are similar to what Brandon covered for bus differential relay protection. The first slope is used to account for proportional errors. So these are due to like the CT errors, the excitation errors, no load tap changer position. We know that we can change that to account for or to provide better voltage regulation for through the transformer, right? And the LTC may be tapping all the time, maybe going maybe changing the turns ratio of the transformer, several percent. So we want to account for that. So that's what that first slope is to account for. So Schweitzer recommends a minimum slope based on this equation. I'm not going to go through how you'd actually calculate that. I mean, you just look at the relay manual for your relay and you determine your slope based on that. But I just wanted to give you a general sense for what that's intending to cover and why you have the different slopes. Slope 2 is to account for transient errors, right? So these are things that are not necessarily continuous, but they're long-term things, right? The LTC is going to change all around. It's not a permanent inaccuracy, say, because it may change from time to time, but it's consistent. It's not a transient issue. Slope 2 is to account for transient issues like CT saturation. If you've done your job, like if it's a new site and you've done your job correctly and you've done your CT saturation calculations and you've sized the CT cables, the conductors correctly such that you don't saturate your CTs for fault current, then slope 2 is kind of irrelevant. You can set it the same as slope 1 because your CTs aren't going to saturate, and so therefore it doesn't matter. But there may be an instance where you're replacing an existing electromechanical relay, and they don't want to run new cable because they don't have drawings for the old cables and they don't know where they are, and the conduit's buried and there's no knowledge of it. They don't know if it's crushed, but they know that the existing conductors work. They just want to put the new relay in the same spot, reconnect the same CT cables. But you look at them and you go, oh, okay, it's going to saturate. It's a really long run, and the CTs are going to saturate for fault current. Well, now you need to look at this, right? So just look for your particular relays recommendations and set the slope accordingly. And again, this is what Schweitzer recommends for that instance. Holy camole. I'm 50 minutes in. I gotta hurry up. Okay, the unrestrained differential element we talked about. It's usually like 8 to 10 times the tap setting. So these are currents that are high enough that you're not going to be operating on the slope characteristic, and you know that the fault is internal because you can't achieve those fault currents, those differential currents for an external fault. Just go ahead and trip. The harmonic blockings, these are really important. I wish I had more time to talk about them. The second harmonic blocking is usually on inrush current. So the first few cycles, because the transformer core is basically a big magnet. You've got the flux flowing around in there, right? And then say the transformer is in operation, and then you open the breakers and take it out of operation. Well, whatever flux was in the core when you opened it up is going to remain there. So it's basically a permanent magnet at that point. And when you close back in the breaker and energize the transformer, it may be that the flux was going in this way, and then the currents, when you close in the breaker, wants the flux to be going this way. And so you get that initial surge to energize the transformer. That's transformer inrush. That can contain a significant amount of harmonics. And so you want to block for those. Follow the relay manufacturer's recommendations or your client standards. Yeah, I wish I could talk about it more. The fifth harmonic blocking, that's for over excitation. Basically, it's volts per hertz protection. I just don't have time to talk about it more in detail. It's not on the homework. That's what it is. So in this case, we would enable the harmonic restraint and enable the harmonic blocking. Okay, per the relay manufacturer's recommendations. And phew, we're done. We've set our transformer microprocessor-based differential relay. Okay, overcurrent protection. I'm going to really have to speed through this. Please review the slides. Give me a call with any questions. Please call, email, text, whatever. I'm more than willing to help answer any questions you have. I don't believe I had any homework problems on overcurrent protection, so I'm just going to try and speed through this. The way I've broken this up is high voltage winding overcurrent protection and phase, and then also for ground. And the ground overcurrent protection is dependent upon the winding that's connected. And if that's not obvious to you right now, hopefully it will be as I go through this. So for your phase instantaneous overcurrent pickup for the high voltage winding, the element should be set greater than either the transformer inrush, which is typically estimated to be 8 to 12 as a worst case of the ONAN rating of the transformer, or the maximum current seen for a through fault on the low voltage winding of the transformer. So there are certain cases where, say that it's a 10 MVA transformer, but there's only 7 MVA of available fault current at the transformer location because it's put into a weak system. Well, you don't necessarily need to set the instantaneous element to account for 10 times the ONAN rating of the transformer because it's not capable of even sourcing that much fault current. So that might be an instance where you look at the low side fault current and take a conservative multiplier on that, 125, 150% of the fault current seen by the high side of the transformer for a low side fault, set it above that, and now you're going to be safe for inrush, and also be secure for low side faults. Make sure you're not going to misoperate. Time over current pickup should be based on the maximum loadability of the transformer. You want to allow the transformer to be fully loaded with any emergency ratings, drastic action limit, long-time emergency, short-term emergency ratings, and you want to be above that. So it's typically 125 to 150% of the transformer's maximum nameplate rating, although sometimes higher values are used. And then the time dial, so that's just to set the pickup level, but then we also need to set the time dial and the curve appropriate such that it protects that transformer damage curve that we talked about during the Aspen one-liner course. And it needs to coordinate with any upstream or downstream protection. And then a note for when you're doing coordination between delta Y transformers, I don't remember if I touched on this or not, but for phase faults for delta Y transformers, the worst case coordination time interval is going to be for phase-to-phase faults. And the reason that is if you have a phase-to-phase fault on the low side, the Y winding side of the transformer, when you reflect those currents up through the transformer to the delta side, there's going to be one phase that is tied to both of the faulted phases on the low side. Say it's a B to C fault, there's going to be one winding, either the B or the C winding, depending if it's a DAB or DAC transformer, that's going to see the fault current for both of those. And so it'll be the square root of 3 higher than the other two phases. So that phase will see current that would be the same if you had a 3-phase fault. So if you have a line-to-line fault, the low side is going to see lower fault current because not all 3 phases are involved. So it's going to be a lower amount of fault current, but then the high side is going to see the same amount of fault current that it would have seen for a 3-phase fault on the low side. Okay, so that has a tendency to crunch those two curves together. Worth noting, a lot of times that gets missed because people look for like a 3-line to ground fault, because it's the highest amount of fault current, and it tends to have that current line further down the curve, decreasing the amount of time. But if you do a phase-to-phase fault, it shrinks those curves together. Worth noting. High voltage winding ground over current, if it's a well, this is talking about how there are different factors. Please review this. If it's a delta connected winding, basically the high side ground over current instantaneous element can, you just need to set it above inrush, which is typically estimated to be 1/3 of the amount of inrush you'd see for a phase element. So if you set the phase instantaneous element to consider 12 times the OA rating of the transformer, then you might set the ground instantaneous element to 4 times the OA rating of the transformer. There's little risk of it misoperating, little to no risk of it misoperating, because the delta winding doesn't allow any zero sequence fault current to pass through it, so you're not worried about through faults. So the area of exposure is really only between the CTs and the transformer winding. And so especially if the CTs that are feeding your relay are within the bushing of the transformer, there is basically no area for there to be a fault that isn't within the transformer. So you can set that low and fast, and that's what we're talking about for the time over current pickup here. The client I'm most familiar with sets their ground time over current pickup to something that's arbitrarily low, like 1 amp secondary, and then just sets it low and fast, and there's little to no risk of it misoperating. If the high voltage winding is a Y grounded connection, typically you don't want to set an instantaneous element, because if there are other lines here off of this bus, this is the high voltage winding in this case. If there are other lines off of this bus, there's no way to differentiate between a close-in fault on this line or a fault on the bus or a fault in the transformer. Those would all have basically the same amount of fault current. So you don't want to set an instantaneous element, unless you do something like restricted earth fault, which is often or sometimes referred to as a 67G or an 87G element. And this is an example of a restricted earth fault element. I've only ever set a couple of these. I don't think they're very common here in the Northeast. Maybe they will be. Some utilities use this very regularly. I haven't seen it that often, but this is what it is. Low voltage winding over current protection, the instantaneous element is typically not applied for the same reason. There's no way to differentiate between a fault inside the zone of protection and then like on the bus or on an adjacent line that is close in. If you set it such that it's secure for an out-of-section fault, then it's not going to operate for an in-section fault. Therefore, there's no reason to set it, and so you just generally don't apply it. And then again, the time over current pickup should be above the maximum transformer nameplate rating, and then you set the curve and the time dial to coordinate with the transformer damage curve and upstream and downstream protection. You usually want the low side pickup to be somewhat less than the high side overcurrent protection. So if you have power flow from the high side to the low side, if the the high side, you want it to be less than the low side. No, vice versa. I had it right the first time. Low side, you want it to be less than the high side because it'll make the low side tend to operate faster. Because you want the low side to operate first for a fault that's out of section. So say the transformer is backing up an adjacent line relay, you want that line relay to operate first, then you want the transformer low side to operate, then you want the transformer high side to operate last. So generally you want the low side to be set somewhat lower than the high side. For Y-connected windings, again, don't apply an instantaneous overcurrent element, and the time overcurrent should be this is a ground protection for a Y winding connection. You want the pickup to be above expected load. So if the system's fairly balanced for that transformer, say it's a 115 kV low side transformer, maybe it's 5 to 10% of the maximum load current. That's a pretty high imbalance. If you set it above that, you're going to be secure. If it's a distribution transformer where you've got half a hundred single phase customers off of one phase and the phases are unbalanced, maybe it's 25, 30% of the maximum amount of phase current, it needs to be above that. And then the curve and time dial are set to coordinate and protect the transformer. And then if the low voltage winding is a delta winding, you can't really set ground protection because there's no zero sequence fault current that's going to flow out of the delta winding. May have to do something else like ground over voltage protection, say. Transformer fuses. This is a picture of the transformer at the Sydney substation. This one feeds my house, so I was jogging by there. I was able to get this picture. Fuses have some advantages. They're cheap, they're reliable. There's little to no maintenance requiring. There's no relaying, battery, control house required. The drawbacks is that they're slow. They need to be replaced after they operate. You can single phase customers. We talked about that during the Aspen one-liner course. I think I just touched on it, but basically, if you have three phase customers on the low side of the transformer, you have a single line to ground fault. I go through an example of this, I think. I'll save it for when I go through the example. The fuses can preheat. We talked about that. You have different K factors that you need to account for due to the preheating of the fuse. If you have a like this fuse transformer here, you have distribution circuits coming out of the substation. If you have a fault, those reclosers are going to close into the fault multiple times. That's going to heat that fuse, and you need to account for that in your coordination study. And then you don't get some of the ancillary benefits like metering, SCADA control, event records, things that are often provided with modern microprocessor-based relays that you don't get from a fuse. This is a couple more pictures of a fuse transformer. So these are the high side fuses, and this is a close-up of what you might see for a transformer fuse. These are spares that they had hanging there so that if one blows, they can replace it easily. This is the criteria going into sizing the fuse. I'm not an expert on this. Usually the fusing is kind of dictated by the client. For this size transformer bank, we use this type of fuse because it generally coordinates in our system and protects the transformer. I just don't have the time to get into this. I've got like 5 minutes, and I got a lot to get through. This is transformer fuse protection to account for the fuse preheating. This is going to be on the homework. This is related to the K factors. So these K factors are applied for load side fuse links. So this is where you have a transformer with a recloser on the low side feeding distribution customers, and that there are different fused laterals that feed customers, right? So if you have a fault here and you have you want to make sure that your recloser coordinates with this fuse after the fuse, as part of the fuse saving scheme. You need to apply these K factors. I think Leo went over this in some detail. But I think he only covered the preheating for distribution fuses. So in this case, you need to apply the K factor to it's always applied to the recloser. The slow curve gets the K factor when you have a source side fuse, which is this instance. And then the fast curve gets the K factor when you have a load size fuse. So this is what Leo talked about. What we tend to use more often in power transformer applications is you have a fused transformer with a low side recloser. And so then if the recloser has, say, a reclosing time of 2 seconds, and maybe you have 2 fast, 2 delayed shots, you would need to apply, a 1.7 K factor to the recloser's slow curve, for example. So depending on what you've got for an application, you need to read through this slide, and that'll help you apply the K factor for your coordination study. Blown fuse detection. This is what I said I was going to say. So if you have a single line to ground fault, or I guess this is a phase-to-phase fault. This is an example from the IEEE guide for protection of transformers. B2C fault, these are the high side currents and the low side currents. So it's a B2C fault. A doesn't see any fault current, B and C do. This is what I was talking about, where the phase that is connected to both of the faulted phases on the low side gets more current than the other two. Okay, so this fuse would see 697 amps for this particular fault, which means that fuse is going to blow first because it sees more current. And then after that fuse blows, it knocks down the current on the low side, but also knocks down the current on the high side. So it's possible that this fault current isn't enough to blow the remaining fuses now that this one is blown. So there's a way to mitigate against that, called blown fuse detection, and it has the ability to differentiate between the voltages that you would see on the low side of the transformer if a high side fuse is blown versus if a fuse in the VT secondary is blown. Those voltages look different, and there's an SEL guideline on how to do that. So I mostly just know that exists. Then there are other ancillary types of transformer protection. I think Adam has covered this already as far as sudden pressure relays. So if there's a fault inside the transformer, you can imagine that there's going to be arcing, there's going to be rapid heating of the oil, and there's going to be a rapid pressure built up in the transformer due to that arcing. And so the sudden pressure or rapid pressurized relay has a diaphragm in it that will detect that rapid pressure increase and expand. And because it's really meant to operate on that rapid pressure increase, eventually that's going to subside relatively quickly. And while the pressure may be higher than normal, it's not actively increasing. So you'd have a seal-in relay. This is an example of that. The sun pressure relay trips the seal-in relay, and that has contacts that are maintained long enough to trip the lockout relay for the transformer. There's also fan controls. Those are looking at the ambient temperature and the temperature of the oil, potentially the ambient temperature, but almost certainly the temperature of the oil or the hotspot, winding temperature. And then that'll allow you to control the fans either manually or automatically based on a thermostat contact. You almost always include some sort of block cooling in your transformer protection if your transformer is big enough to have its own automated controls. And the reason for that is if there is a transformer fault and the transformer catches on fire, obviously that's going to heat up the transformer and you don't want your fans kicking on and blowing air to the fire, or worse yet, there's a rupture in the transformer and it's spewing flaming oil and your fans are just blowing it all over the substation. That's really bad. So usually you have block cooling that's executed by the transformer lockout relay. Temperature detection, controlling the fans, providing warnings for maintenance issues. Gas detection, not to be confused with the nitrogen blanket that may be on the top of the mineral oil if you don't have a conservator tank, keeping that positive pressure that keeps the air out. It's not that kind of gas detection. There are actually trace gases that can exist in the mineral oil itself. Often you'll have the transformer will have like some sort of maintenance schedule where they do monthly or quarterly oil samples, and they'll go to the valve at the bottom of the transformer, draw some oil, and then send it off to a lab to be tested for acetylene or other trace gases that'll tell them tell the transformer owner if there's like corrosion or insulation breakdown and arcing that'll cause those gases to exist in the oil, and then you'll know that the transformer is testing bad, it's failing and is in need of replacement. So that's what gas detection is. There's also LTC controls. We talked about this quite a bit last class. This is an example of an LTC control circuit where you've got a local and remote control. The remote control has the ability to raise or lower, vice versa, raise, lower, or put the LTC controls in auto, or these are control switches in the transformer mechanism housing, so you can put it in manual and then manually raise or lower the transformer LTC position, or you can put it in auto and then the LTC controller automatically raises and lowers it. So this is just an example of the different control switches and a sample schematic that you might have for your transformer LTC controls. There's also transformer paralleling controls. So if you have two transformers that are in parallel and they both have LTC controls, you kind of want those to operate as a unit, because if, say, the voltage gets too low and an LTC wants to tap up to raise the voltage, well, either LTC may tap up. There's going to be some tolerance there. They're not going to operate at exactly the same time. And you don't really want them to operate exactly at the same time necessarily, because if they both tap up, you might get outside of that band and then they both have to tap back down. And that can result in hunting, they call it, where you're trying to always get the voltage back down into the band where it really wants to be is kind of right on the edge, and it just goes up and down and up and down and up and down, and it causes excessive wear on the LTC. So the paralleling controls basically makes it so that the only one LTC operates at the same at one time, and it determines which one should operate based on the circulating current that's flowing between the transformers. So if say one transformer taps up, there's going to be a current imbalance between those two transformers, because one is going to have a different turns ratio than the other. So there's going to be slightly more current in, say, this transformer versus this one based on that tap position. And so there's going to be some of that current that circulates around in the transformer. And what you don't want is those two taps to get too far away, because then you can actually cause excessive heating in your transformers, and that would be bad. So those are the two reasons you want those LTC positions to operate as a unit. These control circuits can get fairly complicated. This is an example from the parallel balancing module the MO115A from Beckwith, and you can see that those get pretty complicated. Mostly just, again, for your knowledge, it's out there. You might have to deal with it. So be aware. And geez, I was able to do it. I'm sorry, it was rushed. But I was able to get through everything that I wanted to cover. Read through the slides. Any questions, concerns, comments, questions on the homework, again, please give me a call, text, email. I'm always available to talk about this or any other topic. I enjoy this stuff very much, so it's no bother. Please reach out. And I guess that's it. This is my last class for this year. So good luck to all of you in your future endeavors. Hope to see you out there in the field, and happy graduation for those of you that are graduating this spring. So thanks again. Bye, everybody.